Welcome to this session. This session, as you can very well see, is on AP Chemistry, Chemical Kinetics, and we're going to get through, hopefully, the first at least 25%, and I'm really aiming for 33%. We'll see how long it takes. I'm happy that you're here. This is one of my very favorite topics. I know that you know electrochem is one of my favorites as well, but I got to tell you, this one comes in a really close second, if not actually edging it out just a bit. I think it's kind of common sense. You've been dealing with rates for a very long time, and when you were in 5th grade, you learned that rate was essentially a change in something over time. And a lot of instances, the change in something was a distance over time. And a lot of kids even call it the dirt formula. But all we're looking at in this chapter is basically a change in something chemical over time. So we may be talking about a change in a concentration of a reactant A over time, where those square brackets, as you already know, mean molarity, concentration in moles per liter. So there's going to be some cool symbolization in this, and if you showed your slacker friends this symbolization, you'd feel all smart and, you know, superior. But that's okay. It works out nicely that way sometimes. But essentially, we're going to talk about what reactions are in terms of their rate and what affects the rate and the collisions that must occur. So this is for mature audiences. At times, some of the discussions are going to get a little violent about these collisions. So let's get at it. Well, as it states here, chemical kinetics is the study of the speed or rate of a reaction under various conditions. So spontaneity, as in delta G spontaneity, is also important, but I don't want you to think that spontaneity implies anything about the speed, because just because it's a spontaneous reaction, it does not imply it's a rapid reaction. So my example is changing diamond into graphite. I'm happy, considering I have a diamond wedding ring, that this is not a spontaneous process. I would be very unhappy to one day wake up and find that my diamonds have essentially been replaced with something that's essentially pencil lead. So it is a spontaneous process, but it's so slow that it's not detectable even in a lifetime or 2 or 3. My ring is from my grandmother, and it's probably every bit of 60 years old, and the diamonds are still intact, I can assure you. We're going to have several parts to this chapter, so I'm just going to give you a little bit of foreshadowing. We're going to study in this session something called Differential Rate Law, and then it has a companion, which is called Integrated Rate Law. If you are a calculus student, these are the same things that you think of as an integral. So if you have calculus abilities, you can use them. We're not going to do that, because this course doesn't require that. We're going to stick with the land of algebra, maybe even some algebra 2. I don't even think we venture into pre-cal, to tell you the truth. So we're going to keep it simple. So those are 2 of the pieces. We're also going to talk about instantaneous rates. We're going to actually talk about that one first. Instantaneous. I have trouble spelling. Instantaneous rates. We're going to talk about relative rates. And we're finally going to talk about calculating activation energies. And you know about activation energies from biology class. You remember graphs that looked sort of like this, or from your first year chemistry class? And in thermo, we talk about that being the delta H value, that difference in energy from beginning to end, where the reactants began, where the products end up. But this right here is the activation energy. And we'll talk about catalysts, and how you learned in biology you could put an enzyme in there, which is a biological catalyst that's actually a protein, and it would lower the activation energy from that really tall hump to a new, much lower value, which is going to speed up the reaction. So we're going to get into some good stuff. We're going to explain some of the stuff that you know only enough about right now to be dangerous. So let's talk about some obvious things. Factors that affect reaction rates. This is common sense stuff. You already know a lot of this stuff. The following conditions affect the speed of a chemical process, one of which is the nature of the reactants. We're going to collide here. We've got to collide. We've got to smack these molecules together like bumper cars, but this time we actually want the bumper car to be broken. So we want to break bonds. We want new bonds to form, and I remind you that it requires energy to break a bond, and energy then is released when new bonds form. We're, in this chapter, solely focused on rate, but don't think for 1 minute that those energy concepts aren't still important. We're just going to spare you some calculations with them. So that's the best news I'm going to tell you in the next hour. Okay, so some reactant molecules react in a hurry, others react very slowly, but physical state plays a part. If you've got gasoline in the liquid state versus gasoline in the gaseous state, this is dense, and this is much less dense. So if you're talking about collisions, gas molecules are not going to collide with each other since they're not very crowded in a given space compared to liquid molecules of the same substance. So with solids, often you get no reaction at all because only the surface area of what you would physically smack into another, like taking two crystals of these things and smacking them together, which is silly. But if you did that, you're essentially not going to get any reaction. What we really need to do is get these into the aqueous state. So liquids and aqueous, things that are dissolved in water, reactions are going to be the most effective. The chemical identity also plays a role. That's the word I was searching for, a role. So what is it actually reacting? Usually we have ions of opposite charge, and those react very quickly because we got Coulomb on our side. So they have Coulombic attractions, because you know that opposites attract your teenagers. Usually, the more bonds between reacting atoms in a molecule, the slower the reaction rate. So if you have substances that are doubly bound, triply bound, they're going to have a much higher reaction rate than things that are all singly bound. Because you've got to break more bonds if you're going to separate the atoms so that you can recombine them into new substances. Also, if we have single bonds with really large bond energies, things that are glued together, like the hydrogen atom to the oxygen atom in water in that HO bond, these things are going to react much more slowly. So some examples are metallic, like metallic sodium reacts much faster with water than metallic calcium. The oxidation of methane can be increased if you increase the temperature. You're going to hear me say heat them up and speed them up a lot. Which is Texan for heat them up and speed them up. So heat them up and speed them up. So photosynthesis, for instance, is a very slow process and changes very little with an increase in temperature. So concentrations of reactants. Again, it's all about these violent collisions. The more molecules you have, the more collisions you'll have. Imagine running down the hall in the middle of your math class. There's nobody in the hall, right? Everybody's in class. No one would be lurking and hanging out in the hallway with a hall pass. They're all in class, excited to be learning. However, if it's passing period and you try to run down the hallway, you're not going to escape without some bruises. Maybe even like some serious, like on the floor kind of collisions. So the more molecules we have, the more collisions we have. So the concentration definitely matters. A 1 molar solution is way more concentrated than a 0.1 molar solution. So again, with the temperature, heat them up, speed them up. My symbolization is a little messed up there, but I fixed it on your copy on the wiki page if you are getting your notes from there. The faster they move, the more likely they are to collide. So if you're walking down the hall at passing period, you're probably still going to bump into somebody because most people don't watch where they're going. But if you're running down a crowded hallway during the passing period, you're going to have way more collisions, perhaps even an injury. But an increase in temperature is going to produce more successful collisions. I want to talk about successful in just a minute, that are able to overcome the needed activation energy. That's that hump on that diagram up there that we drew earlier. This one, that one right there. And that means we're going to have a general increase in reaction rate, which is code for it goes faster with increasing temperature. So let's talk about successful collisions. For a collision to be successful, it has to have the proper geometry. Meaning top, bottom, side, side. It doesn't do you any good to put these molecules together upside down, let's say. If they have a direction to them, they have they're not perfectly symmetrical. They have what you might consider a top, a bottom, a left, a right, a plus, a minus. Call it what you want to call it. It's just different. One side's different from the other. So must have a proper geometry, which we often in textbooks talk about that as orientation. The orientation those objects have in space. And then secondly, it must have sufficient energy. Sufficient energy. The collision has to be violent enough to transfer enough energy into that bond between two atoms to break it. And so you might think of this as the oomph It's a fabulous science word, the oomph. So are these molecules hitting in the right orientation, and are they hitting with enough energy, the right enough amount of oomph when they hit each other to actually cause a bond to break or a bond to be made? It works both ways. Energy and orientation are the two biggest factors in whether these are what we call effective collisions. So you've heard of free response questions. You're going to have to write about some of this stuff. And orientation, effective collisions, sufficient energy are all phrases that you need to put into your explanations if you're being asked about what factors could increase a rate of a chemical reaction. So, in fact, a general rule of thumb is that speeding them up gives them more energy, and that this is something you really should know. I promise you really should know this. This is one of the little factoids you should memorize. A 10-degree increase in temperature will effectively double the reaction rate. Just 10 lousy little Celsius degree increase will make the reaction go twice as fast. So yes, if you double it again, if you raise it 10 more degrees, you'll double it again. It'll be 4 times as fast as it was 20 Celsius degrees ago. So that's important. And this does have a little bit of a caveat that it does depend on the magnitude of the activation energy and the temperature range. We can't get insane about this, because if we get into super high temperatures, we may be melting things, which means all bets are off. You change the states, or we may be decomposing things thermally, stuff like that. But in room temperature kinds of conditions, in laboratory conditions, if you increase something by 10 degrees Celsius, a reaction that's going on in a beaker, then it's going to effectively double the reaction rate. And we're going to do a lab with this, hopefully. Hopefully your teachers are going to do the crystal violet lab with this. I've got some video, and I'm going to do a different video. I think that's redundant, but I'm going to do another recording, we'll put it that way, on that lab, so that even if you don't get to do that lab in class, you'll still be able to see what I'm talking about. And then our fourth item are catalysts. These are things you know the most about because you've had biology most likely. And so a catalyst is something that speeds up or accelerates a chemical reaction, but they themselves are not transformed. So you may have learned the definition: a catalyst is neither a reactant nor a product, but speeds up a chemical reaction. That's how we usually teach it in middle school, maybe even 9th grade. But now you're big kids, and it's time to learn a little more about it. It's not enough to just be able to recite the definition. You need to understand how it works. So you were first introduced, most likely, to enzymes, and those are biological catalysts that are actually protein in nature, which means they have an amine group and an acid group, because you know that they're made up of amino acids. So they're fairly sizable molecules. Way bigger than like just a chunk of metal, like the platinum metal that's in the catalytic converter of your automobile. A catalyst is a substance that changes the rate of reaction by altering the reaction pathway. And it's going to do this in a couple of different ways. Think of the catalyst sometimes, especially in a biological system when you have an enzyme involved, as like the band director out on the field. And the band director is going, wait a minute. You flautist there, you are marching the wrong direction. Turn around. You trombonist, you're off by 10 degrees. Go to the right, 10 degrees. You're tilted wrong. So basically a catalyst is drawing the reactant molecules in, and it's positioning them through electrostatic, again that's code for plus minus, attractions, so that it's basically shoving around the reactant molecules so that they are in the proper orientation. When they're in that proper orientation, now we just have to worry about getting the proper energy, which temperature is our friend in that regard. So catalysts work by lowering the activation energy, and that makes our collisions more successful because they're meeting these two criteria that we talked about: orientation, sufficient energy. So the catalyst, again, is not part of the chemical reaction. It's not used up during the reaction. It can get saturated. You can have all of your enzyme molecules busy and have more reactant molecules than enzyme molecules, in which case that could make you start off really fast and then kind of slow down, but it would still be faster than it would if the catalyst wasn't there, it being the reaction. They can be homogeneous in one state, like a piece of metal, or like the platinum I was talking about earlier, or they can be heterogeneous, like they are in the case of enzymes. For example, H2O2, that's hydrogen peroxide to you. Somewhere in your house or in your school or in the grocery store or in the drugstore, you could find a bottle of hydrogen peroxide that would be stored in brown plastic. It's relatively slow to decompose into water and oxygen. It's the oxygen that would make the bottle explode because the gases take up so much more room. However, if you expose this to light, hence the need for the brown bottle in the first place, if you expose this to light, it's going to accelerate this process, and with the help of something like manganese dioxide, it'll go extremely fast and be ever so exciting and messy. You'll get foam everywhere, especially put just a little dab of dishwashing liquid in it. Your teacher may have done a demo for you in first year or lately called elephant toothpaste. If not, you should request it. It's actually a really cool demo. But what a catalyst does, once again, is lower the activation energy barrier. Don't stop there. That's not enough to know. It lowers it by providing a surface for more effective collisions, by allowing for proper orientation of the molecules, so that if it's warm enough, they will have energy sufficient enough to make or break bonds. So therefore, this is the important part, the forward and reverse reactions are both accelerated at the same degree. In other words, it's an equal opportunity catalyst. Whether you're talking about the forward reaction, which when I said earlier, we typically think of these as reactants and these as products, but you know reactions are reversible. And so if we talk about the reverse reaction, we'll be headed this way up the graph. And so if I put in a catalyst that's going to lower the amount of energy needed for this reaction to take place, I'm telling you, it works this way. That's the forward reaction that you're used to. And it works this way in the reverse reaction as well. But I still go to the dotted line, so that's what I mean by it's an equal opportunity catalyst. So to the same degree means I don't go up all the way to the top on the reverse reaction. So some homogeneous catalysts actually appear in the rate law because their concentration affects the reaction. And so you're going to see that when we start writing rate law expressions. The surface area of the reactants. This is the common sense one for you. In temperature and surface area are the two most common sense methods. You know that if you want something to go faster, you often heat it up. And you also know that if you want something to go faster, like dissolving a sugar cube into a glass of iced tea or a cup of warm tea, if you pulverize that sugar first and make it more granulated, it's going to dissolve faster. So surface area of reactants, when you have exposed surfaces, that affects the speed in a good way. So except for substances that are in the gaseous state or solution, reactions occur at the boundary or the interface between two phases, which is why solid plus solid, not so great. Very slow reactions, if at all. The greater the surface area exposed, the greater the chance of collisions between particles. So the reaction should proceed at a much faster rate. So if you live in an area like in Virginia where there's a lot of coal mining, and even parts of Texas where there's a lot of coal mining, coal dust is very, very explosive. Dust is a bad thing down in a mine shaft because if somebody lights a cigarette or there's a spark from a metal tool on another piece of metal or anything, it could ignite that carbon. Now, that's what coal essentially is, and burn it, and that's going to cause a big explosion, and it's not a good thing. Grain elevators, like grain, wheat, you know, you've heard of grain. Grain elevators, that big storage tanks out in rural areas, also have this problem because if there's dust and hot days and such, you could really have a bad accident. So if you consider coal dust versus a piece of charcoal, a huge difference in the rate of reaction. If one's explosive and the other one, it takes a lot of effort to actually get it to light up at all. If you've ever watched somebody try to grill on a grill, which is a charcoal grill, not a gas grill, a charcoal grill. But solutions, things that are aqueous, that's what we deal with the most because we get lots of exposure between those molecules or ions that are floating in that aqueous solution, and they can collide quite readily with each other. And then this is a fave, just a fave of the AP exam. Don't fall for it. If you add an inert gas, there is no effect on the rate or equilibrium of the reaction. Why not? I know you people. Curious sorts, you. Why not? That's because when we start writing rate expressions, they're going to come at us in this format. Rate equals some constant times concentration of one reactant, two reactants, however many more we have. I'm going to call them A and B for lack of imagination, raised to some power. Okay, yes, I did just say power, which means exponent. So, point being, if I add anything into this mathematical equation, like an inert gas, it's not a reactant. It's inert. Inert, lump on a log, inert, does nothing. Inert, has lots of inertia, just sitting there. So it's not going to be in this math. If it's not in the math, it can't affect the rate. It's just as simple as that. Don't overthink it. All right, so what we've sort of gotten a start on is what we call collision theory. So according to collision theory is a nice way to start some of your explanations in free response when you're having to write sentences about this stuff. Use the big people word, collision theory. I'm putting them in quotes for you. Particles must collide. Normally only 2 particles collide at once. It's really hard to get 3 to collide simultaneously with the right orientation. Speaking of orientation, proper orientation of colliding molecules has to happen so that the atoms in the can or in the container can come in contact with each other to become products. The collisions have to occur with enough energy. Think oomph, don't write oomph, write enough energy to overcome any electron-electron repulsion, since you're bumping cloud to cloud here. There's going to, all those negative electrons on the surface are going to repel each other, so you've got to overcome those repulsions. And the reacting species must have enough energy to transform translational energy into vibrational energy in order to penetrate into each other and their electron cloud so that the electrons can rearrange and form new bonds. I realize that sounded very dirty, but in essence, what we're saying is molecules move from hither to yon, and that's translational. But what makes bonds happen involves more vibrational energy. And if you can transfer the energy of translation, that moving from one point to another, into vibrational energy, then you're going to vibrate that shared pair of electrons completely out of position, and I know you like my sound effects, that bond breaks. And when that bond breaks, it's because you added energy into it. When a bond forms, you get energy back out of the system. All right, so this new collision product is going to be at the peak, the top, the tippy top of this diagram with this big giant hump on it. And it goes by several names just to mess with you. Activated complex, transition state, because you know grown-ups can't get along. You've heard that speech before. And that activated complex or transition state at this point can either fall backwards, which is just a pity because all that work and nothing's going to happen. It's going to go right back where it started. Or it could go this direction, actually form a product if that is what you seek. So when all of these criteria are met, the reaction can proceed in the forward direction. So it's really sort of amazing that we have any reactions occur ever at all. It's a real shame if they get to that activated complex stage and fall right back over to undo everything that had been done thus far. So let's get to the good stuff, because you noticed, I know you have noticed that my little pink calculator is not up yet. Ha ha ha, never fear. You see that equation, you see that numerator, you see that denominator, you know it's coming, don't you? So let's get to the math part. Chemical reaction rates. The speed of a reaction is expressed in terms of its rate. We already talked about that, change in some measurable quantity over time. The rate of that reaction is measured by the decrease in concentration, because we love our molarity, so think molarity, think mole per liter. Your book may use either symbol. So we can have a decrease in concentration of a reactant. How come, how come, how come? Because reactants are disappearing. Or we can have an increase in concentration of product. How come, how come, how come? Because products are appearing in a unit of time. So when writing rate expressions, we can write them in terms of reactant disappearance, which we were, guess what, going to put a minus sign on it, because their concentration is dropping, decreasing, or product appearance, which started off at 0, and so you guessed it, we give that a positive sign. So rate is not constant. Well, okay, it can be on occasion, but it's really rare for rate to be constant. That's what I should say. It changes with time, which means you've entered the land of curves. Y equals mx plus b is still your friend. You're just not going to get your friend very often. So we're going to graph a lot of data in this chapter. Graphing the data of an experiment is going to show you an average rate of reaction. You can find the instantaneous rate. Focus on the word instant, rate at an instant. So instantaneous rate by computing the slope of a straight line tangent to the curve at that time of interest. I'm going to translate that into English and actually make it visual for you. So let's talk about this green line. I got this reaction, and that's NO2. I know it's small on the screen, and I know it's kind of fuzzy, but that's NO2. I know that that is a reactant. Think about it. Think about it. How do you know that's a reactant? Well, there's a 0 right there. And I've got concentration in moles per liter. I realize again it's small, so think this is molarity on this axis. And I have time, our good buddy time. Matter of fact, any time you see time on the x-axis, you have entered the land of rate, no matter what course you are taking. 7 of the 12 required biology labs are rate labs. This can translate over to some good biology points too if you're in AP Bio. Physics, oh yeah, the whole first semester is all about rate. Some of the second semester too, come to think of it. So NO2, I know that this is a reactant because we had some when we started. And as time goes by, its concentration decreases. There's a 0, like I said, right here. So the purple line and the blue line are representing NO and O2. And so those are both products. So without cheating and looking down the page, I know that this equation is NO2 is producing NO plus O2, and that's not balanced. Double this, and we're balanced. All right, so one more time. Rate's expressed as the change in concentration of a reagent per unit time. So the word rate is symbolically often represented as a change in something over a change in time. And the rate of a reactant, like I already said, is always positive. The rate of change of a product is always negative. And if we want to find out the rate at any instant of time, I'm going to clean this up a little bit. And I want to know at 100 seconds. Because see, that said time in seconds right there. So at 100 seconds, I can tell you what the rate is there, and there, and there. So at 100 seconds, you draw a tangent line, a line tangent to that one and only by definition point. There's only one tangent line there. And then you simply calculate slope, rise over run. If I wanted to know it here, oh, and by the way, notice that that slope equals rise over run. Rise is your y-axis. That would be concentration of NO2 over a change in time. That'd be a change in its concentration. And so slope is equal to rate. Don't overcomplicate that concept. Slope is equal to rate. Notice that it has a negative on it, hence the reason we put the negative sign on this expression. So if we're talking about NO2, it would have a negative. If we're talking about one of the others, you're about to see why they would have a positive. Do the same song, second verse. Draw the line tangent to that curve. Come over. Do your rise over run business. That slope is going to be the rate, and notice it's a positive slope because we have nowhere to go but up. And finally, third verse, tangent line, calculate the slope. Pick some points, do a rise over run thing, and you're going to have the rate at that point. Note it's also positive. Note that these two lines, the oxygen line and the NO line, are not equivalent. Note they do not have the same coefficient. Stoichiometry matters. I know that shocks you. So what we're really saying is oxygen, as you can see by the purple line on this graph right here, that oxygen can appear only half as rapidly as the nitrogen dioxide disappears, while NO is appearing twice as fast as oxygen disappears. In other words, you have to respect the stoichiometry. So this is essentially in text telling you exactly what I just talked about. Examine the data table. Calculate the average rate at which NO2 changes in the first 50 seconds. And remember the square brackets are shorthand for molarity. So I would take that rate is equal to the negative, note the negative because NO2 is our reactant. The negative change in NO2 over a change in time. So if I look back up at that data table, .0079. See the .0079 minus the .01 where we started. So we're looking at these 2 points right here. The difference in them divided by the amount of time that took, which was 50 seconds. So the difference would be a negative 4.2 times 10 to the minus 5 moles per liter per second, which could look like this. That's faster to write. Or it could look like this, which is very annoying. Or it could even look one other way. It could even look like mole liter to the minus 1, second to the minus 1. Nope. Yep. I gotta think about that. Yep, that's right. Molarity per second. Molarity per second. Yep, that's it. Equals 4.2 times 10 to the minus 5. But notice that the minus of the minus thing canceled out. In this example, it doesn't always work that way. All right, so note that rate is not constant, but like we said, it decreases with time. So what we just did, these are going to give us average rates. Notice all of them are multiplied by 10 to the minus 5. One must learn to read headings of data tables in this chapter, or you're going to regret it. So to determine the value of the rate at a particular time, which we call the instantaneous rate, again I say for the final time, and I'm going to quit beating this horse, compute the slope of a line tangent to the curve at that point, and pay attention to the signs. New topic. Relative rates. That means they relate to each other. So we can consider the appearance of products along with the disappearance of reactants. The reactants concentration obviously is declining, the products is increasing, and we're going to respect the algebraic sign and the stoichiometry. So we're going to divide the rate of change in concentration of each reactant by its stoichiometric coefficient in the balanced equation. If you do it this way, it's foolproof, and this makes this really easy. So I'm going to tell you one more time from the top that we're talking about this reaction. We're talking about the same example. So our reaction was 2 NO2s decomposing into O2 and 2 NOs. What we're saying with this line right here, starting right here in the bracket, is make the coefficients denominators. So that's an understood coefficient of 1, and that's 1 over 1, which is a good old 1. And this becomes 1/2 as well. So that this will be disappearing, hence a negative sign. These are both appearing, hence a lack of negative sign, which is an understood positive sign. So if you don't like the fact that I've got 3 different expressions, you would never use all 3 at once. You're only going to pick a pair. So we can do this for however many reactants and products. You're only going to relate the one thing that you measured to something else in the reaction. So don't freak out over this long line right here. You're not ever going to use all of it. You're going to always just pick a pair and relate to them to each other. So again, why is this a minus sign? It's a reactant. These are plus signs, understood it the way they're printed on this page, because they are products. You're making some. You started with none. The negative sign here means it's disappearing, decreasing. If you don't like the fractions at all, then multiply through and get rid of them. So if I multiplied every one of them by the same number, and that would be the number 2, then I get 2 over 2, which is a minus 1. I get 2 over 2 with a positive sign, which is plus 1. So this would be a minus 1, this would be a plus 1, and this would be a plus 2. All right, so fair enough on that. Again, all we have to do is take the coefficients of a balanced equation. That's going to be 1. And put a 1 over their coefficient, and we would have minus 1/4 times the change in the concentration of pH3, I think that's phosphine, but don't quote me, divided by time, plus 1, there's an understood 1 there, the concentration of the allotrope, P4, over a change in time, equals plus 1/6 the concentration of hydrogen gas over a change in time. And you would relate any 2 of these to each other, hence the words relative rates. So what are the relative rates of change in concentration of the products and reactant in the decomposition of nitrosyl chloride, NOCl? Well, can you apply this pattern is all this is getting you to do. Sure you can. Sure you can. Pause me. Pause me, and I want you to write this format into this little box using these critters right here. Go ahead, I'll wait. I'm still waiting. I really want you to pause it. I really want you to write it. I'm trusting you. Okay, you should have written rate equals minus 1/2. How come? How come minus? Because it's a reactant. Concentration of NOCl over a change in time is equal to, these are kind of like conversion factors from dimensional analysis days, concentration of NO over a change in time, which is equal to just 1, the change. I left my change off of that one, didn't I? Ooh, I left it off of that one too. Ooh, bad example. Change of CL2 over a change in time. So I need those deltas in there. So I want you to lock onto the fact that the word rate can be symbolized by any one of these things. The equal signs really are mathematically equal to each other. So if you know the rate, because you figured it out a different way, like, I don't know, the way we're about to learn differential rate law, and they start then asking you about the rate of a different critter in the balanced equation, this is the technique that you will use to answer those questions. This is easy. Speaking of easy, this is more like a logic puzzle. So those of you who sort of enjoy logic puzzles, or puzzles in general, you're actually going to really like this. Okay, so differential rate law. This is what I really want to get through, and I'm doing pretty good. I'm about halfway there. Reactions are reversible. Yeah, we've established that. So far we've only considered the forward reaction, but the reverse is equally important. And the truth is that when the rate of the forward reaction is equal to the rate of the reverse reaction, we have achieved equilibrium. That would be your next major unit of study, because, you know, we like segues like that. And so you need to know that definition. Sooner or later, your choice. But to avoid this complication, because this gets really messy once we start having some of the reactants converted to products, but yet they can collide with each other and go backwards and go right back to reactants, because forward reaction, reverse reaction, all going on at the same time. It's like, you know, unorganized, complete and total chaos in that beaker. So to avoid this complication, and you're going to be so happy about this, we discuss reactions soon after mixing and talk only about initial, right out of the starting block, reaction rates. So we don't worry about how messy it gets with the buildup of products and all of that. You get to do that later in college, like about the time you're a junior in college. So no worries, this is going to be a breeze. So initial reaction rates begin with pure reactants. You mix up the pure reactants thoroughly, and then you figure out a way to measure the speed of reaction over time, and your eyeballs are not your best tool. We either talk about changes in temperature, number of bubbles of gas, and one we're probably really most fond of is color change, because we get some color change in this unit. It's kind of fun. So the presence of products, again, could alter those results dramatically and lead to very confusing results. So we're going to talk, again, initial reaction rates throughout the rest of our discussions. So, new symbolization. We've already covered this, the word rate, and we've already covered this concept of this must be a reactant minus change of NO2 over change in time. Here's the new part. Differential rate law looks like this. Rate equals a rate constant, K. This is a baby K. I need you to write it as a baby K, because that equilibrium chapter we're going to do next, loaded with big capital Ks, and we need to be able to tell the difference in your handwriting to score you properly on the AP exam. So, times the concentration of, I only had one reactant in that initial reaction we had the graph for earlier, and that was NO2. But if I had several reactants, it would be in the form of rate equals K, A, B, C, keep going, however many. And then where our job is going to be is to do an experiment, analyze the data, and figure out what these bloody exponents are supposed to be. It's not hard, I promise. I know it sounds scary, but it's not. Trust me. We have to build up a little trust by now. So the rate expression or rate law expression, like I said, and y'all, oh, the worst moment of my teaching career. Yes, I am Texan, and I did get a y'all in there. The rate expression or the rate law mean the same exact thing. My students came back from the AP exam one year and said, oh man, we thought we knew kinetics and knew it really well, and all the questions kept asking for rate law, and we didn't know what that was. We only knew how to do rate expression. I wanted to die. I wanted the earth to open and swallow me and just never let me out. It was awful. So please understand the questions mean what you think they mean. Some books say rate expressions, some books say rate law. Just like this word. You may not have that word in your textbook, but some books have it and some books don't. But I want you to know it in case it ever comes at you and you won't be afraid of it. So differential rate law, rate expression, it all means this format right here. So we're going to have this literal mathematical equation that we can calculate rate when we start changing concentrations of either A, B, or C, and we're going to figure out from the experimental data the value of K, and it's going to be just a big old fun fest, puzzle solving moment. So, how will you know when to use this? You'll know when to use this when you have been given a table that has concentration data and rate data. And remember that rates are a change in molarity over a change in time. Concentration is the molarity. So you're going to have tables that have molarity, 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 molarity for every reactant, and then it'll have the word rate, or this symbol to mean the word rate. Your job is to figure out what the exponents are and to also put it into rate equals K, concentration of reactant, concentration of reactant, concentration of reactant, exponent, exponent, exponent form. Lots of practice coming at you. All right, so what the differential rate law or rate expression does is it generally depends on the reactant concentrations. And to find the exact relation between rate and concentration, you must, I love the word must, you must conduct actual experiments. Think science fair. You must conduct experiments and collect information. If you see something hovering above an arrow, which you may have seen this before, that if you put a triangle up there, that usually means to heat it, as if that were the sad attempt to draw the flame on a Bunsen burner. But if you see something hovering above here like light or radiation or platinum or manganese dioxide or anything else, then that is a catalyst, and it does end up in the rate law. So be sure you plop it in there. Don't leave it out just because it's not technically a reactant. It is participating in a reaction by providing that surface that's going to make more effective collisions and such. So you do want to have that in there. So initial reaction rate, which we typically are too lazy to write, and we just write the word rate, equals K, again I caution you it's a baby K, times reactant A, reactant B, and because there's a catalyst present, we put the catalyst in there as well. And then, I don't know why MNP, it could be ABC, but that would be redundant with the ABCs we already have. It could be XYZs, but you're looking for the values of these exponents. Call them what you wish. M and N, P, I don't care what you call them. Just call them something. And K, like I said, is the rate constant. That's its name. Obviously, the in brackets A, B, and C are our reactant concentration in molarity, which is what moles per liter. And then again, the order. Okay, let's talk about that word for a minute. I didn't make this word up, I promise. Order. My hypothesis is it's sort of like the fact we talk about being off by an order of magnitude. Like if I had 0.1 versus the number 10, and I wrote this as 10 to the minus 1, and I wrote this as 10 to the 1. The difference between here is 2, because we went minus 1, 0, and 1. So that would be off by 2 orders of magnitude. I don't know if the word order has come from that concept or what. And I don't, it's just what we call it. I don't have the historical background on that, and I wish I did. If you Google it or find it, somebody let me know. I'll put it in somewhere. I'll give you credit. So M, N, and P are these little exponents up here in the rate law. Enough said. It's easier. This is one of those things that's kind of easier to do than it is to explain. So those exponents, those orders, can be 0, whole numbers, or fractions, which you will see very rarely. But 1/2 is not that uncommon, which would be a square root, so that does show up from time to time. But again, I say, must be determined by experimentation. So the rate constant itself is temperature dependent. If you change temperature, you change K values. That's the only way you can change K values. And it must be evaluated by experiment. So temperature dependent. So in a simple example of rate equals K times the concentration of reactant A, and K has a value, now note, okay, let's talk units for just a minute. Rate, K, concentration of A. And we're looking for that order. What is rate measured in? Molarity per time. It's a change in molarity over a change in time, so it's a molarity per time. K is a number, and its job is to make the units work. So what is the significance of those square brackets right there? Ooh, that's a molarity. So I have K sitting here times M. How are these units ever going to work out? M, numerator, M over 1, understood, numerator. Got it. But what's going to happen? How am I going to get that little per time in there? Well, it goes here. So your K values will always have a time unit. Now what I just did was first order, as if this exponent were 1. Agreed? That's 1 molarity. Oh, but let's have molarity squared. So that would be molarity squared. But that's a lie. Now you've violated the 11th commandment. What thou hast on one side of an equation, thou must have on the other. I remind you that K is simply a number. But right now, the units on my right side of the equation are molarity squared over time. How are you going to get it just molarity over time? Think about it. Think about it. Pretend I'm your 9th grade algebra teacher. Okay, maybe 8th grade algebra teacher if you're really smart. How are we going to get the right side of the equation to be a single molarity over time? Well, if you've never seen Welcome Back, Kotter, this will mean nothing to you, but you need to see Welcome Back, Kotter. There's this thing called Nick at Night or TV Land. You need to find Welcome Back, Kotter. It's all about high school classrooms up in the Bronx, I think. And there was a kid on there named Arnold Horshack who would go, oh, 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 I know the answer, I know the answer. So the smart ones among you are going, I know the answer, put a molarity down there. Now this molarity would cancel that square off, and you would have the total right side of the equation cleaned up in molarity versus time, molarity per time, and check, that works. So units on K are there solely to make the whole right side of the equation end up molarity over time. You're going to have to get used to this. We'll do lots of examples. This will feel better in about 10 more minutes. All right, so we've talked about the order of the reaction. There is an overall order, so this is the lingo you have to master. The order with respect to a certain reactant. Reactant A, hydrogen peroxide, nitrogen monoxide. The order with respect to a certain reactant is the exponent on its concentration term in the rate expression. The order of the reaction is the sum of all the exponents on all the concentration terms in the expression. So if I had A, B, and C, 1, 2, and 3, the overall order, this is not a trick question, add them up, what would it be? Go ahead, use all your fingers and toes. 6, you say with resounding fury. Indeed, it would be 6. 3 plus 2 is 5, plus 1 more makes 6. So that would be the overall order of the reaction. So read the questions carefully. So let's determine how we're going to do this and what these things mean. We talked about the fact that these exponents can be 0. We also talk about the fact this is an initial rate, right out of the starting block. So these little O's can mean at times 0, if you want to think of them as a 0, or they can mean the letter O as in original. It's your call. I've seen books do it both ways. 0 order means that the change in the concentration of a reactant has no effect on the rate. Let's think about that mathematically for just a moment. Rate equals K, concentration of A to the 0 power. I recall Mr. Thomas in 9th grade teaching me that any number raised, or any quantity raised to the 0 power was a big fat 1. So indeed, I'm just multiplying by 1. That's not having any change on the rate at all, is it? Rate equals rate in that case, or in this case, rate equals K. So these are not very common, as you might imagine, that you can double and triple and quadruple concentrations of reactants and not have much happen. So the general form of the rate equation is rate equals K. First order means exactly that there's an exponent of 1, so rate would equal Ka. Nuclear reactions, decay reactions, usually fit into this category. So it's pretty common to have exponents of 1, and it's pretty common to have exponents of 2. So, I should give a little more time to this. I'm sorry, let me back up just a minute. What this first order means is the rate is directly proportional to the reactant concentration. If you double the reactant concentration, think of a 2 in there for a doubling, then wouldn't you get 2 rates? And if you put a 3 in there, and you raise it to the first power times K, wouldn't you get 3 rates? Because K is constant, its number's not changing. So whatever you do to the concentration, that's exactly what's going to happen to the overall rate in the case of a first order reaction, or reactant for that matter. And then second order is exactly what you would think. If I stick with this 2 up here, that means that's going to be squared. If I stick with that 3, that means that's going to be squared. So wouldn't that be 4 rates? And wouldn't that be 9 rates mathematically? So if the rate is quadrupled when the reactant concentration is doubled, or increases by a factor of 9 when the reactant concentration is tripled, then it is second order. So they're common, particularly in gas phase reactions, to be on the lookout for them. The general form of the rate equation is rate equals Ka squared, or Rate equals K, A to the first, B to the first, which would have an overall order, again with that word, 1 plus 1 is 2, an overall order of 2. Fractional orders, like I said, do occur, but they're rare. So one more time, a recap before we get down, and I'm going to have to bring up my calculator. Recall our general rate expression. Rate equals K, A to this exponent and this exponent. They use different letters so you don't think they're the same, because we have to actually analyze data to figure this out. So if m equals 0, this is the lingo you have to adopt, because you have to explain these exponents on a free response question. So if the exponent, or m if you prefer, is 0, the reaction is 0 order with respect to A. So what we're saying is if m was 0, the lingo to talk about that is the reaction is 0 order with respect to A. If m were 1, it's first order with respect to A. Get it? If m were 2, the reaction is second order with respect to A. Get this with respect part? Because you're going to have to write that. If n is 0, same song, second verse, reaction is 0 order with respect to B. If n were equal to 1, it's first order with respect to B, and if n were equal to 2, the reaction is second order with respect to B. So I can put any combo of these things that I want, and I talk about this, what I just wrote, is second order with respect to A, first order with respect to B, third order over all, because 2 plus 1 is 3. I know that somebody told you chemistry was hard, but I think they may have misled you. So when we add the orders of each reactant, we get that overall order of the reaction. All right, our first example. Ooh, makes me happy. Ooh, clear that screen. Has nothing to do with this. Okay, let's focus on this. There's two ways to attack these, but I'll tell you right now, you're going to get a table of data, and you got to decide which method you like best. I have a favorite. I don't want to prejudice you. I just am all about speed and accuracy and visualization of chemistry and chemistry concepts. So for me, what I lovingly call table logic, hence the quotes, it's a phrase I think I've coined, but I may have picked it up subconsciously somewhere else. But basically, I'm not going to do a whole lot of calculation and canceling and, make this the big old mathematical expression that stretches all the way across my page. I am way too lazy for that. I'm going to use the brain the good Lord gave me. So, when you look at experimental data and you have two concentrations going on for two different reactants, in other words, this looks like A plus B yields a product. I got way too much going on. I wish this was a single reactant, but it's two different reactants. So I'm guessing you've done a science fair project at some point in your life, and if you'd done one for me, there would have been 50 repetitions minimum if you wanted to make a 70 on the project. But you wouldn't have done this in AP. You would have done this earlier than that, like in my sophomore level class. But if you have two reactants, you better hold one constant while you vary the other, and then a well-designed experiment would, go ahead, drum roll, indeed, hold constant what you varied and vary what you had held constant. So I'm looking at this data table, and I'm looking for a couple of trials where something was held constant somewhere, and I found them. I actually like this and this line the best. And the reason for that is I really like to see a concentration of something doubling, which I write 2x to imply doubling, while the concentration of the other folks, the other reactants, are held constant. And the reason for that is because I'm probably not as mathematically gifted as you are. On my good days, I can multiply by 2, divide by 2, square 2, and on my very best days, I can even cube 2. So I'm always on the lookout for a concentration that doubles. I don't always get it, but I'm faster if I look for this. This is going to take some practice on your part. I ain't lying to you. This is going to take a little practice. But what I'm starting with is I'm looking for the two lines of data, which are experiments numbers 1 and 3, where B's concentration was held constant at 0.2 molar. And I like to draw this little arrow from trial 1, or experiment 1, to experiment 3. The concentration of A was doubled, and I ask myself, what did the rate do in response to that? Well, dang, it didn't change. It stayed the same. So if you double the concentration of A and the rate doesn't change at all, boo-boo, nothing changed, then I know this so far. Rate equals K, concentration of A to the 0 power. Now, if you want, I can prove that to you again. Let's use lines 1 and 2. Let's use these two. Still held constant. That's the key. You can't do this without holding something constant. Well, you can, but it gets messier. That's not the number 2. That's 1.5, isn't it? Yes, it is. That's increasing the concentration of A, experiment 1, 2, experiment 2, TWO2, 1.5 times. What'd the rate do? Not a dadgum thing. So I'm convinced this is 0 order. So it's not a bad thing to try twice if you're not 100% sure. All right, now what? Again, you can rewind me. You can listen to that again. If you're going, huh? What is that crazy Texas lady talking about? You can rewind, start over. Not to the beginning, just this piece. All right, now what am I looking for? Now I want A to be held constant while I double B. If I could have exactly what I want in a perfect world, that's what I want. Ooh, found it. There and there. I'm happy. I'm happy. Hold A constant, double the concentration from 0.20 to 0.40. What did the rate do as a result of that? I'm asking myself, what is the change here? This was doubling. Got it. 0.2 to 0.4. That's doubling. What happened here? 0.5 doubled to 1.0. It also doubled. So that means this is first order. We'd already figured out it was 0 order with A. So it is first order with B. So I finish this off. And you can put the 1, you can not put the 1. It's an understood 1. You're going to see me put it just so that I am crystal clear if you're not paying 100% attention. You look at this later. So there is my first order in B. Okay. Now, all of that was just laid out here for you in text. Look for 2 trials where the concentration of a reactant was held constant. Next, focus on the other reactant. Ask yourself how its concentration changed for the same 2 trials. Was it doubled? Was it tripled? Was it halved? That's a hard word for a Texan to say. Once you've determined the factor by which the concentration of the other reactant was changed, then determine how that affected the rate for those same 2 trials. Expect easy math. Did changing the concentration have 0 effect on the rate? If so, then it's 0 order. That's what happened to us in the case of A. We changed it, and nothing happened to the rate. So B was held constant here, 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 here. 0.5, 0.75, 1.0, nada, nada, nada. So it has 0 effect. Did the rate double when the concentration of the other reactant was doubled? And if so, it's first order. And did it quadruple, etc., etc. So if you're still struggling with this, what I mean by when I say it doubled, if you're thinking about rate equals K concentration, and I doubled the concentration of something, it's twice as big as it was. And I'm asking, what is that exponent? And I analyze the data, and I see that this also is a 2. Then doesn't this exponent have to be a 1? And that's first order. If this became a 4, because the rate quadrupled when I doubled the concentration of the reactant, wouldn't that exponent have to be a 2? Yes, indeed. If I tripled the concentration of the reactant, and this were triple the rate, we're back to 1. If I leave it, the concentration of the reactant tripled, and this were 9 times the rate, wouldn't that make it 2? If I triple it and the rate doesn't change and it just stays the 1 rate value that it was, doesn't this have to be 0? If I lost you, rewind me, listen to it again, pause in between, think about each one, and see if you can figure this out. If you feel hopelessly lost, then you may want to keep just listening, because we're going to repeat, repeat, repeat several times. You'll get a clean slate here in just a minute. All right. Think of the concentration doubling, like I said, as the number 2. That's what I just did for you up top. So rate equals K times the reactant becomes rate equals K times 2, double the reactant. And you're trying to determine the value of M. If the rate doubled, think 2 rates is equal to K, 2, M. More simply, 2 equals 2 to the M power, so M's got to be 1. If the rate quadrupled, then think simply 4 for the rate side is equal to that doubling of the concentration to a power, and that power is M, and it must be equal to 2 to make that a true statement, and so on, and so on. So finally, we want to examine the data table again, and this time do the opposite. This time look for a trial where the concentration of the reactant you just determined the order for is held constant, and then just repeat those 3 steps above. For our example data, the rate stays the same regardless of the concentration of A, therefore we determined it was 0 order. However, the rate doubles with a doubling of B, it triples with a tripling of B, and that indicates that the exponent on B is first order. So again, the 1 is optional. You can see in this text it wasn't printed there, but the fact you wrote it down means you had 1. So the summary, then, when you are writing the rate law, the rate expression, is to write rate equals K, A to the 0, which you can leave out, okay, like especially in the AP exam, B to the first, which can also look like this, because this is a big fat 1, A to the 0, and you don't even need that 1, so this could also be a correct answer. So the overall reaction rate order is 1 plus 0, or first order overall. Now, the next thing we're going to be asked to do is find K, solve for K. So I'm going to come back up here where I had the numbers visible. I'm going to clean it up a little bit, just so we're not as distracted by all that red. And I'm going to go to green, so that your brain will know this is a new step. You want me to calculate the value of K? No problem. K equals rate divided by concentration of B. Because this is a big fat 1, that's all I got, is the concentration of B. So in my class, I would have you in like 4 different groups, 5 different groups, 5 different rows, whatever. Row 1 would take experiment 1's data, plug and chug. Row 2, experiment 2. Row 3, experiment 3, etc., etc. And then you'd all come up with the same number anyway. You'd be all frustrated because I'd accuse you of cheating when the second group gave the same answer as the first group, and by the time I get to the third group, you're looking at me suspicious, like I've lost my mind and I need more caffeine. But by the time we were done, you'd realize, oh, the constant is constant. As long as all of these experiments were conducted at the same temperature, we're going to get really, really numerically close to the same value of K for each one. So pick a line, any line. Pick your favorite, doesn't matter, just pick one. 0.50 times 10 to the minus 2. Look at the heading, look at the heading. Molarity per hour divided by, don't need any of this, it's not in the rate law. All I need is B. So divided by 0.20. I just used the first line, and that is molar. So my molars are going to cancel, and my rate constant number I'm about to come out with is going to have just a per hour. So K equals 0.5 second EE minus 2 divided by 0.2. 0.025 per hour. And you can use HR if you like, but I think H is actually the official abbreviation for hour, just like S is the official abbreviation for second. But with minutes, it's MIN. Okay, so indeed, that's what we got. 2.5 times 10 to the minus 2 is the same as 0.025. You're scientific notation literate. All right, so you're going to get the exact same value with any line of data. That's the exercise I would have put you through in class, is we would have been in different groups. Like I said, everybody would have calculated. The first group would have said, I got 0.025. I'd have gone, oh, okay. Moved on to the second group. Well, I got 0.025 too. Cheaters. You disgust me. Move on to the third group who's now afraid to say anything, and they're kind of looking at me suspiciously. And they're, we got 2.5 times 10 to the minus 2, thinking they could trick me. And then by the time I got to the last ones, they'd be on to me and go, isn't it a constant? Aren't we all supposed to get the same thing? Yes, indeed you are. Now, sometimes you don't want to do the table logic method because maybe something wasn't held constant. I'm going to show you some examples where that's easy enough to do in the next recording. But sometimes you just kind of want to cop out and just do the algebra method. It takes longer, it takes more to write, it's slower on multiple choice, but it works like a charm. So it's completely up to you. I take the entire expression over the entire expression, and I crank out an answer. I can pick any lines of data that I want, but you're smart if you select a trial where one reactant concentration is held constant so that that term drops out of your math. That's just going to speed you up. So you still want to look for data where something is held constant. So looking back up here at the top, I know you have it in paper format. But looking back up here, A is 0.5, 0.75, while B stays 0.2. And that's a good plan so that the 0.2s are going to cancel out when you put them one over the other. Or the 0.5s in this case, as it was. So 0.5 times 10 to the minus 2 for the rate divided by 1 times 10 to the minus 2 for the next rate of the next line of data. This is using trials 1 and 4 of that data table. The constant is the constant, so it drops out. If you're smart enough to pick something where those concentrations are held constant, they drop out. Now it comes down, oh, and that drops out too. So what you really get is 0.5 over 1, which is lovingly called 1/2. And you should recognize 0.2 over 0.4 as 1/2 as well. And that's raised to a power. What must the power be? Must be 1. So you can write all of this out, or you can just explain it in table logic. It's just the longhand mathematical version of just looking at it and doing some of that math in your head. It's completely your call. All right, I've been talking at you for about an hour, which means my file size is getting large. So I'm going to end right here and come back and start again right here. And we'll pick up with this concept because that's a good breaking point. In the next recording, you might want to hang around and do it. Maybe not right now because you're probably about ready to vomit, but we're going to work through just those last 2 boxes in your lecture notes, but I have a new surprise for you. You have an AP worksheet that your teacher may or may not be using in class, but we're going to work through pieces of them, not all of them. I'll do that elsewhere. That's the button I'm looking for. But we're going to look at just the tables that have come off of real AP problems, and we're going to solve for K. We're going to talk about the units on K. We're going to get the orders down. We're going to get good at this. So if you're already good at it, sayonara. If you're not, then come on back and listen a little more, and we're going to just simply look at these data tables and these data tables and these data tables until we get dang good at determining the orders, determining the rate law, calculating the value of K, and determining its units. If you can do just that on a kinetics problem, you're in danger of beating the national mean. And if you beat the national mean on every free response and can pull a really good multiple choice score, you're going to make a 5. But I'd rather you smash the mean to smithereens and buy yourself a little insurance, because this unit, it's really pretty easy. And so I hope you come back. Signing off. Thanks for your kind attention.